the number system, I have discussed you decimal number system, binary number system, octal number system, hexadecimal number system. Even though, if I go in a detail, so we can say that there is a decimal number system which usually human understand, and we use this number system in day-to-day life, and we have 10 symbols in this decimal number system. So it's a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 10 decimal number system usually used in the all uh, mathematical calculations everywhere in day-to-day life. So the decimal number system having the base or radix is 10, and the digital position is usually used in the integer and fraction number system. So in this case, whenever we have a position, particular number position, so that position is uh, used to calculate the weight of the digit. Okay, and when we multiply digit with the weight and we do the summation of the digit multiplied by weight, will finally calculate the magnitude of the number. So suppose we have a number like this 512. So the position of this particular number 2 is 0, position of this number 1 is 1, and position of 5 is 2. So over here, when we go in the fraction toward the right side, so from the uh, right side of the fraction, we can see that the 7, digit 7 having the power, position minus 1, because it's a from point toward the right side. Okay, and digit 4 having the position minus 2. So we can say, we can calculate the weight. So it's a 0.1, 0.01 for the 7 and 4 respectively. Similarly, 1, 10 and 100 for the 5, 1, 2, 5, 1 and 2. Sorry, 2, 1 and 5 respectively. So we can, when we sum up this all digits, or when we multiply digit with the weight, respective weight of the digit, we can, and we sum of all the digit multiplied by weight, we will finally get the 512.7 in the decimal, and we can write like this in a small bracket with the base 10. If we talk about the binary number system, so the binary number system, we can say having the two symbols 0 and 1. In binary number system, you can see over here the B from the binary and ITS from the digits. Okay, so it will finally calculate, finally termed as a bits. Bit means a single symbol of the binary system. Okay, usually the binary system having the base 2, and with the position we can calculate the weight. The bit multiplied by weight will give you the sum of the bit multiplied by weight will give you the magnitude of the number. And in this case, usually when a group of 4 bits are there, it is represented as a nibble, and group of 8 bits represented as a byte. Over here you can see that suppose a number is given in the binary 101.01, as we have discussed earlier, that this will give you the position. Okay, and this is the position in the form of the fraction 1 by 2, 1 by 4. Okay, so it will be, when it will multiply with the magnitude, it will give you 5.25 in decimal. This representation, please just note down this thing. This particular representation that we are seeing is in the form of this, that we are observing in the sham color, that is in the form of binary, and the black color notation is the binary equivalent decimal, that is 5.25 in the decimal. This is also a method how we can calculate binary to decimal conversion by multiplying magnitude, by multiplying weight of just discussed recently that group of 4 bit, like this, will be presented as a or say it is called as a nibble. Similarly, group of 8 bit represented as a byte. Okay, so this is all about the binary number system. And the octal number system, when a number system having 7 symbols. In the previous case, in the decimal we have 10 symbols, in the binary we have 2 symbols, and in the case of the octal number system, we have 8 symbols starting from 0 to 7. Okay, so in this case, the base is 8, and as we have already discussed, weight will be calculated based on raised to position, and whatever weight is there, that is, if it is multiplied with the digit, and we sum up the uh, all the digit multiplied by weights, then we will get the final magnitude. You need to remember that the final magnitude is in the form of the decimal always. Okay, so this magnitude that we are calculating, that is the decimal representation, but the 512.74, that is the octal representation. Okay, so the octal representation over here, we can say that this is on the position 0. So 8 raised to 0 is 1. 8 raised to 1, the, the weight is 8. 8 raised to 2, the weight is 64. Similarly, over here, that is minus 2. 8 raised to minus 1, it's a 1 by 8. 8 raised to minus 2, that is 1 by 64. Now, whatever weights we have, we just multiply with the digits. So 5 multiplied by 8 raised to 2. Similarly, all the numbers are multiplied, and when we sum up these numbers, we'll finally get the uh, magnitude, that is the 330.9379375 in the decimal. But the equivalent is again still same, 512.74 in octal. So you have to remember that this is the binary, this is the decimal representation, and this is the binary, this is the octal representation. Even we can represent these things in the form of binary numbers also. There is a separate conversion is there. We will discuss this particular thing in the next slides. The last and very important number system, that is the hexadecimal number system. The hexadecimal number system actually used in most of the modern computers to represent the group of bits. Over here, you have to remember that the octal number system is a group of 3 bit, because if it is 2 raised to 3, 2 raised to 3, if I calculate a weight, so if it is a 2 raised to 3, then it can represent 8 symbols. So this is the group of 3 bits. Okay, and it is made up like that's why it is called the octal number system. But the standard one is the 16-bit number system. Over here, there is a difficulty is that we have like we can represent numbers in 0 to 9. We can represent number in 0 to 9, but we don't have a representation from 10 to 15, because it is a number system with the base 16. These are the symbols of the number system. You have to remember that these are the symbols of the number system. Similarly, if we see here, okay, in the decimal number system, we have a representation from 0 to 9. So these are the symbols. That's it. Similarly, over here, these are the symbols of the binary number system. Similarly, over here, in the octal number system, we have symbols from 0 to 7. 8, 9 are not considered as a part of the octal number system. They are not valid symbols of the octal number system. So you have to remember this thing. Similarly, in this case, we have a 0 to 9. 10 symbols are there, but the rest of the symbols are represented in the capital letters from A to F. Over here, you have to understand that F is a 15, 14, 13, 12, 11, 10. So A is a 10. Even though you have a question that we can we can represent 10, 11, 12, 13, 14, 15. But there is a difficulty again. It is not a unique symbol. It's a combination of the symbols. If I represent 10, so it is a combination of 1 and 0 from the number system, and they are represented differently. So over here we want a unique symbols, and that unique symbol is A, B, A for 10, B for 11, C for 12, D for 13, E for 40, F for 50. Okay, so in the hexadecimal number system, hexa means 16 and decimal means having the decimal representation. Okay, so this is the hexadecimal number system. So the number system with the base 16. So in the this hexadecimal number system having the base 16, and according to the position we will calculate the weight. So for that you can see here this particular, suppose a number, suppose I have taken number, suppose I will take a number 1E57A. So if we start with the from the from the Mentesa point, from the left side, so very first number is a 5, very first digit is a 5, and the position of the digit is a zeroth position. This is the zeroth position. This black color is the zeroth position, and the weight of the number or say digit 5 is 5, is a 1. Okay, similarly if E is there, E, okay, so E is a 14, so 14 having the position first, okay, 1 position, and the weight of the E is 16. Similarly, the when we have a number like the digit 1 over here, the position is 2 and the weight is 256. From Mentisa, if we go to, like if we move toward the right side, okay, so from the Mentisa, so this is the position -1, this is the position -2, so accordingly 1 by 16, 1 by minus 1 by 256 is there. So these are the weights of the hexadecimal digits that is given over here. And when we multiply them, suppose 1 multiplied by 16 raised to 2, okay, 14 multiplied by 6. Now you have to understand that though it is written E over here, but the value of E is 14. So you have to multiply 14 with the 16 raised to 1. Similarly, 5 multiplied by 16 raised to 0 plus 7 multiplied by 16 raised to -1 and 10 multiplied by 16 raised to -2. And when we sum up all this, sum of the digit multiplied by weight, we will finally find the 485.4765625 in decimal. You have to represent, you have to remember that whenever we calculate the magnitude will be always in the form of, is always in the decimal form. Okay, and again hexadecimal format is written like this: 1E5.74. Okay, and over here base is 16. So this is the hexadecimal number system. So you can see, even you can see that when we try to evaluate the magnitude, the binary to decimal conversion is there, and again we can revert back. Similarly, the octal to binary we can go anytime. Just to evaluate the magnitude, we have to always represent the thing in the decimal. Okay, and rest of the thing you can convert from decimal to octal. Similarly, you can convert from decimal to hexadecimal. There are various methods are there. Even we can directly represent binary to hexadecimal and hexadecimal to binary, binary to octal, octal to binary. Similarly, hexadecimal to octal and octal to hexadecimal by making appropriate groups. Okay, so this is all about the number system of the uh, that is supported by the computer, like modern computers. Okay, so that's all about the number system.